Hello, everyone. This is Carlos Pimentel from Mexico, and I'm going to present the research I developed during my PhD in Spain related to computational aerodynamics. The title of this presentation is Development of a Three-Dimensional Vortex Method for Solving Detached Fluid Dynamics. As you can see, this research is based on our interpretation of the potential flow theory. First of all, I would like to briefly introduce myself in order to put my work into perspective. As I said before, I am currently a PhD student in an aeronautical engineering program at the Polytechnic University of Catalonia. I have experience in experimental aerodynamics, having carried out tests on small parachutes and satellite TV dishes at the National Polytechnic Institute in Mexico. I also have experience as a user of CFD software based on the finite volume and lattice Boltzmann methods, mainly to perform aerodynamic simulation on parachutes, UAVs, full-scale aircraft, and rockets. During my master thesis, we developed a Lagrangian mathematical model for a payload parachute articulated system to perform a dynamic and stability analysis during its descent phase. Furthermore, I have experience in the design, manufacturing, implementation, and testing of a small parachute for various applications, including UAV and sounding rocket recovery. If you want to know more about this, I invite you to visit my personal website. It is now time to define the general objective of this research, which is to develop a pure Lagrangian velocity-vorticity-based computational code for the accurate solution of fluid flow past three-dimensional shell bodies, or in simpler terms, plates. Such a method must be developed from a strictly numerical point of view, avoiding the use of any semi-empirical approximations or ad hoc corrections. Furthermore, the input parameters must be reduced to a minimum in order to limit their dependence on the results and to reduce the complexity of the numerical analysis. At this point, the current version of the final code requires only 6 input parameters. It is important to emphasize that at this stage of development, numerical accuracy must take precedence over computational performance. I will now describe the specific objectives of this research. The first is to develop simpler codes in order to understand and analyze in detail their numerical behavior as a function of input parameters and spatial and temporal discretization. The first corresponds to the two-dimensional unsteady discrete vortex method, or UDVM, described in the well-known book Low-Speed Aerodynamics, written by Professor Joseph Katz and Alan Plotkin in 2001. While the second corresponds to the two-dimensional full vortex cloud method, or FVCM, described in detail by Professor R.I. Lewis in the book Vortex Element Methods for Fluid Dynamic Analysis of Engineering Systems, published in 1991. The code for the latter is available for downloading on github.com, as well as the following methods described. The second specific objective is to develop a more complex vortex lattice scheme from a simple one. The simpler scheme is the standard vortex lattice method, which only includes wake detachment along the trailing edge. A more complex model is shown in the corresponding figure, which includes detached lateral wakes and is able to give a good approximation, at least for the lift component, for low aspect ratio configurations in the low angle of attack range. On the other hand, the full multi-wake vortex lattice method, or FMVLM, is a basic model to consider the flow separation behind the plate under straight wakes and implicit assumptions. Such a final model has been obtained after applying a strict methodology to maintain consistency in the scope of potential flow and vortex lattice approaches. Further details of this development are provided in the relevant part of this presentation. The final specific goal is to extend the full multi-wake VLM to its unsteady version, the unsteady full multi-wake vortex lattice method, or UFVLM. This is a critical step because such an algorithm will form the basis for future time-domain implementations. Therefore, the verification and validation phases must be carried out with particular care, maintaining the same development philosophy as before, precision and extreme attention to detail rather than performance. Finally, a vortex particle-based version is achieved through the full nonlinear vortex tube Porton method, or FTVM. Such a novel numerical method reveals fundamental aspects of fluid dynamics that were previously obscured, such as the physical mechanism of leaf and drag generation. Now it is time to briefly introduce the subject of this presentation. Potential flow theory is defined by the Laplacian equation, which is a second-order linear partial differential equation containing the Laplacian operator and a scalar potential function. The vectorial velocity field u, which depends on the x, y, and z directions in Cartesian coordinates, can be obtained from the gradient of the potential function phi. A classical visualization obtained by solving the Laplace equation can be observed in the upper figure, when the flow path is perfectly defined, rounding the effort along the calculated streamlines. Mathematically, a potential flow is defined as a rotational or vorticity-free by applying the rotational operator to the velocity and setting it equal to zero. Moreover, a potential flow can be incompressible or compressible, so it is not limited to having a divergence-free field. But in the context of classical potential flow theory, we consider the first assumption. This is the subject of the present research. The supposed implicit assumption of a potential flow is in no way mathematically defined. The absence of fluid viscosity nu in the formal definition does not in itself mean that such a flow is implicit, and strictly speaking, it is not possible at this point to define anything related to this particular property. Note that the definition of a potential flow defines fields, but not a physical property such as viscosity. To demonstrate that the current interpretation of a potential flow models a viscous fluid, I will refer to the well-known D'Alembert paradox, a classical problem where the drag component is absent for a two-dimensional circular cylinder immersed in an ideal flow, defined as an irrotational, incompressible, and inviscid fluid. The first thing to remember is that the Reynolds number is simply the quotient of the inertial and viscous forces. The first figure shows a physical test for water, a naturally viscous fluid passing a circular cylinder at extremely low speed, corresponding to an extremely low Reynolds number. As expected, the water shows a laminar flow pattern on the surface of the cylinder. The other figure shows a potential flow simulation, which surprisingly produced the same streamline pattern, although it is known, or perhaps not, that potential flow theory models under an infinite Reynolds number condition, as confirmed by several renowned fluid dynamists. Unfortunately, I cannot go into more detail here, as time is limited for this presentation, but I invite you to read a short blog article entitled A 4-Question Quiz on Fundamentals of Fluid Dynamics to analyze this subject more deeply from an observational point of view. Vortex methods are a family of Lagrangian-based numerical methods developed to approximate the Navier-Stokes equation in their velocity-vorticity form. As you can see, the pressure field drops out after applying the rotational to the total time derivative of the velocity field, which is a huge advantage in not having to deal with such a term. Since it does not appear in the definition, the flow solution does not depend on pressure. However, it can be reconstructed a posteriori if necessary. In such an equation, the first term on the right-hand side corresponds to vortex stretching, while the second corresponds to viscous diffusion. By their nature, vortex methods do not require to subdivide the space occupied by the flow, as do alluring methods in a more conventional computational fluid dynamics approach, such as those based on finite volumes. For this reason, it is less computationally expensive because, like all particle-based methods, it only needs to calculate the flow variables at certain and sufficient points of interest, than in the entire surrounding space. But what is the relationship between potential flow and vortex methods? Well, vortex methods need to be fed with a precisely amount of vorticity detached from the entire surface of the object in order to solve accurately. This is where the current development is relevant. It provides the current amount and orientation of vorticity to the surroundings without forcing an attached viscous flow assumption, which should be the base model to solve fluid dynamics from a purely meshless approach. Aspects such as vortex strength or stretching, viscous and turbulence effects can also be accounted for by such numerical methods. More complex aspects such as compressibility and thermal effects can be solved in the near future as the development of this new approach continues. The first article has been published in a first quartile journal called Advances in Aerodynamics. The full multi-wake BLM is the result of a numerical well-founded procedure that basically consists of adding groups of wakes to the simplest model, the single trailing edge wake or standard BLM, shown in figure 17 with number 1. Another well-known model is shown with number 2, which allows the separation of the lateral or wingtips wakes and gives good agreement for low aspect ratio configurations, but is limited to the low angle of attack range. The next step, shown in number 3, is the addition of the leading edge vortex, which is numerically justified by a counterintuitive rotation, since it is analyzed within the pre-stall condition, where the leading edge vortex wake remains attached to the plate, as has been experimentally observed. For the post-stall condition, a logical and intuitive rotation must be expected. However, such a model will solve a cavity case, as concluded in the present research. Number 4 shows a multi-trailing edge wake submodel, which is very similar to the detached circulation scheme in the linear code developed at NASA in the 90s, shown in the figure just below. In number 5, the leading edge vortex wake has been added to improve the previous results. The next model, shown in number 6, is actually the full multi-wake BLM, in which external and internal vortex wakes have been included in order to capture the three-dimensional effect of the flow, which was limited in the previous models. As you can see, this is the chosen base model for future implementations within the present research. A detailed scheme of such a model is shown in figure 12. Finally, in number 7, the leading edge vortex wake has been removed in order to model a rounded leading edge instead of a sharp one as in the previous case. It is now time to show the validation case for a quadrangular flat plate. In figure 22, it can be seen that the full multi-wake BLM is in perfect agreement with most of the experimental reference data for the lift coefficient in the medium to high angle of attack range, where it is assumed that viscous effects are negligible. On the other hand, for the low angle of attack range, where viscous effects are assumed to be important, the full model without leading edge vortex or with a rounded leading edge agrees quite well with the experimental data, while the full multi-wake BLM, which according to a precise verification, it tends to agree with the linear analytical result as the discretization increases, represented by the black dashed line, which is by definition an implicit result. Note that the difference between the analytical and experimental result is due to the contribution of the fluid viscosity. Figure 25 compares the drag coefficient calculations for the low angle of attack range. As can be seen, the full multi-wake BLM agrees perfectly over the entire analyzed range. It should be noted that such an analytical solution is based on a linear lift coefficient calculation, and therefore cannot be extended to higher angles of attack under a low perturbation assumption. Experimental data are shown only for indirect comparison, as they include the viscous contribution. The corresponding publication also shows the result obtained for the pitching moment coefficient, which is also in agreement with the expected results. Figure 19 shows a bounded circulation distribution on the plate at an angle of attack of 20 degrees. It is clear that the circulation, and hence the vorticity, is concentrated towards the leading edge of the plate, as determined experimentally, with a well-defined leading edge vortex. In simpler models, such circulation tends to be concentrated on the other side, towards the trailing edge, assuming that the fluid remains perfectly attached to the surface. It is shown graphically that such simplified models must be avoided for high angles of attack when attempting to model a detached flow condition. Other validation cases can be found in the relevant publication, including side lip cases and a different shape, as shown in figure 30. The second article in the series was accepted for publication in the journal Computer Modeling in Engineering and Sciences after a particularly difficult review process, because it is the most difficult to explain and understand, especially because it requires more effort to analyze it from a complex algorithmic perspective. However, its publication is crucial as it is the basic model for future and steady implementations. Figure 6 shows a symmetric full multi-wake roll-up behind a 4x4 discretized flat plate at a given angle of attack, obtained by the unsteady full multi-wake BLM following a strict methodology to achieve the highest possible numerical accuracy. Two versions of such a method have been developed, the original and the improved. The former was useful during the verification phase, while the latter was useful during the validation. The difference between them lies in the treatment of the first wake row. In the original version, such a row is fixed and aligned to the free stream velocity, while in the improved one it can adapt itself according to the instantaneous flow solution, becoming a more accurate scheme. Both are schematized after the first iteration in Figure 4, where the red filaments correspond to the original, while the blue ones correspond to the improved version. Since the particular publication is the densest in terms of numerical analysis, detailed explanation of the verification and validation phases will be avoided in this presentation. Figure 5 compares unsteady lift and drag coefficients for different angles of attack. The main characteristic of such numerical results is that they converge to a steady-state value quickly. In Figure 8, the same aerodynamic coefficients are compared by including vortex stretching and vortex core radius corrections. There are some notable numerical differences. Figure 11 shows the comparison between the original and improved version of the UFVLM for a single angle of attack. Some differences are also evident. Now, it is time to talk about the validation phase. Figure 14 shows both steady and unsteady numerical results that agree with an angle of attack range, as is the case for the single-wake steady VLM and its unsteady version, the UVLM. This means that the unsteady versions practically replicate the aerodynamic coefficient behavior of the steady version. As you can see, this particular method is not able to capture the aerodynamic characteristics along the entire pedestal range. Note that slight differences between the results obtained by the original and improved versions are due to the orientation of the first wake row, as shown in Figure 15. Figure 16 and 17 show a strange wake pattern where the first wake row is artificially extended downstream to obtain the correct aerodynamic coefficients. This paper concludes that such a problem is related to the choice of filaments or tubes to discretize the vortex wake, especially for configurations where there are strong wingtip vortices. By choosing spherical elements for the discretization, such a problem is avoided, since these types of element induce the velocity in a radial way, whereas the previous ones induce it around an axis, thus obtaining higher induced velocities in the surroundings. As you will see, the method presented next and its result explain such a fact. The last article in the series describes a vortex element method that combines vortex tubes and Bortons to discretize the vortex wake and bounded vorticity on the plate. It is fully based on the concept of the full multi-wake BLM and the unsteady full multi-wake BLM algorithm. The main contribution of this numerical method is to obtain a perfectly stable method by allowing the numerical conservation of both circulation and vorticity through a novel vortex stretching scheme based on the temporal variation of vortex volumes with time. Such a scheme is a well-justified calculation described in the corresponding publication. However, it requires special effort and time to explain it in detail. For this reason, only a brief description is given here. Figure 9 shows the conceptual idea behind the hybrid cylinder-sphere scheme used in the present numerical method, where a vortex element is defined by a vector with circulation and an associated volume, represented by a tube or a cylinder. At the same time, such a tube can be represented by a sphere with the same volume. As a wake vortex tube evolves over time, it can expand or contract under the action of the total velocity field, but according to the conservation laws, its volume must change from one instant to the next. Thus, the vortex squeezing stretching term is solved by such a cylinder strain, while its induced velocity field is obtained by its corresponding spherical element or Borton. The same process occurs with the remaining wake vortex elements at each time step along the entire simulation. Figure 13a shows the bounded and wake Bortons with their corresponding vortex filaments for a flat plate for a 2x2 element discretization at an angle of attack. The lighter spheres represent the bounded vortices, while the darker one represent the wake vortices transported downstream after one iteration. As can be seen, the present method uses a single wake Borton per filament scheme. In Figure 26, the Bortons have been removed for better mesh visualization in a higher discretization case after 30 iterations, where the wingtip wake roll-up just appears. Figure 10 shows a mesh independence analysis for a flat plate based on the convergence of lift and drag coefficients for different discretization at three angles of attack. From such plots, it is clear that the smooth solutions are obtained in all cases, which, regardless of the extreme attention to detail in its implementation, can be an indication that the method has been coded correctly. Further results will confirm this. Figure 11 shows the numerical results of the lift, drag, and pitching moment coefficients for inviscid flow past a quadrangular flat plate discretized by 16 by 16 elements, from 5 to 45 degrees of angle of attack. Such steady values are plotted in the figure 12 and compared with at least 3 sets of experimental data, since no analytical solution exists. It should be noted that this is the first time that such a level of precision has been achieved using a vortex method for this particular type of simulation, as previous tries have attempted to obtain it using simplified detached vorticity models. Finally, figure 13 shows the vortex wave pattern for the 40-degree angle of attack case, with the vortices colored according to their strength. Additional validation cases can be found in the corresponding publication. This section presents the main conclusion of this research, but the full set can be found in the corresponding thesis document. Current numerical methods based on potential flow theory, commonly known as panel methods, inherently model a bounded and thus viscous fluid condition due to their circulation vorticity attached to the surface scheme, including an infinitely thin boundary layer. Thus, a detached flow condition cannot be modeled or solved under such an attached circulation vorticity approach. In separated fluids, attached boundary layers do not exist. The steady full multi-wake vortex lattice method, or FBLM, is the basic model for circulation vorticity numerical methods for the accurate solution of inviscid detached flow path bodies. Its premise is extremely simple. Several small plates share their wakes to the proximity and give the aerodynamic characteristics of the wall plate, including the inviscid drag component. Any simplified detached circulation vorticity scheme does not correctly model a continuous media phenomenon such as incompressible aerodynamics. By detaching the vorticity only from the external edges of a plate and general geometries, it solves for a cavity case, including a vacuum behind it, resulting in incorrect pressure distribution and external force coefficient calculations. In the pre-stall condition, the leading edge vortex in a shell body has a counterintuitive rotation. This allows to explain why the leading edge contributes to the generation of forces, including lift. On the other hand, within the post-stall condition, an intuitive leading edge vortex rotation is present, and such a sign change helps to explain abrupt loss in lift after the stall point, since such an edge no longer contributes to the external force calculation. The full nonlinear vortex tube Borton method, or FTBM, is a fundamental unsteady scheme for solving the Euler and Navier-Stokes equations in their velocity-vorticity formulation through pure Lagrangian mechanics and conservation laws. Its extension to general geometries and more complex phenomena, such as compressibility and thermal effects, should provide an efficient alternative for meshless computational fluid dynamics. Since the pressure field is decoupled from the flow solution of the Navier-Stokes equation in its velocity-vorticity form, the induced velocity field is the main cause of fluid attachment or detachment, but not the favorable or adverse pressure gradients. The pressure field is a consequence of the velocity field, not the other way around. This is clear in the dynamic pressure equation, where the dependent term is pressure and the independent term is velocity. The resultant force vector acting on a body immersed in an inviscid fluid is a consequence of the induced velocity field developed by the evolution of the vorticity field, detached from the entire surface, then advected and diffused in the viscous case. This holistic approach answers a fundamental aspect of fluid dynamics. How is lift and drag generated, or why do airplanes fly? The mathematics behind potential flow theory is clear. The supposed inviscid flow property do not appear explicitly. Irrotationality does not imply inviscidity per se, since according to the theory of vorticity generation mechanism, a rotational field is generated near a surface in a non-viscous medium. Lift and drag are not aerodynamic forces per se, but the vertical and horizontal projections of the resulting force vector. Therefore, any hypothesis or theory that attempts to explain only one of them, as if they were independent, must be incomplete. Numerically, the resultant force generation has been satisfactorily explained and justified by the present research. If you have any questions or would like to know more about this research, please feel free to contact me through any medium. Thank you for your time and attention.